Hi everyone. I'm usually actually walking around, that's why I had the simples. It's very difficult to stand in one place and talk like that, but I will try to do my best. So I will be presenting you something on Smooth. And Smooth is the package that I've been working on for the last few years. This is the Hex sticker, and I have them with me. If you're interested, I can give them to you. What is behind Smooth? The official title is Forecasting Using State Space Models, and it implements single source of error state space models for purposes of time series analysis and forecasting. So this is the stuff that is written on CRAN. Quite boring, isn't it? The motto of the package is to give more flexibility to user, and it is currently version 2.5.1 on CRAN. Now, some of you might have questions like, why do we even need this stuff? Because we have a forecast package, we now have a Fable package and other nice forecasts related packages on CRAN. Well, in order to answer this question, we need to go back in time. Let's say October 21st, 2015. That was the time when I was doing my PhD. I was quite young. I was thinking that I need to save the world. And as you see, I didn't even have a beard back then. When I was doing my research, I realized that when I use exponential smoothing from forecast package, I'm missing some elements. For example, I needed multiple steps ahead loss functions in order to optimize my model slightly differently. I needed explanatory variables and had some issues with initialization for my specific purposes. So I faced that problem, and the question was, what should I do in these circumstances? And obvious as any other sane person would do in this conference, I decided to develop my own exponential smoothing in my own package. It took me quite a lot of time, but here we are now. So what does Smooth include right now? What functionality it has? Smooth actually stands for, was originally, the name came up because of the exponential smoothing. But then after years have passed, it has changed. Now we have more models there. So we have exponential smoothing in ETS framework developed by Rob Heinemann and colleagues. We have intermittent demand state space model. We have two types of ARIMA models, state space and multiple seasonal ARIMA. We have vector exponential smoothing, and we have some other things. Now, there is a lot of different functions in the package, and it would take, I don't know, several hours to actually explain everything. So I decided to go do something like case-wise. So we will have a look at several cases and see how we can solve the problems using Smooth package. Here are some links to the posts on my website. They cover different topics on the Smooth. So if you're interested, you can go and read about that. Now, we start with fast-moving products. Fast-moving, those that we face every day. So an example of sales of, let's say, beer, weekly sales, and we have some series like that. It's quite difficult to predict. Even by looking at it, you see that there's probably a lot of things happening. Maybe there is some seasonality, but also we have some data from the company, and they say that there are promotions happening. So the blue line, or whatever it is one type of promotion, the red one is another one, and green is the third one. And we can see that in some cases there is influence of promotions, in the others there isn't. But for example, the red one seems to be increasing our sales all the time. So we would want to take this information into account, and probably also take into account that the demand might change over time. That's why we might need or want to use exponential smoothing with explanatory variables. We also have some prices of the company, and it's a bit more difficult to see, but for example, sales sort of have some relation with prices, right? So we have a set of variables, and it would be also nice to somehow select those that are useful. So what do? We start with something simple. We start with exponential smoothing. We say that here the sales, our model is quite simple. It's multiplicative error, multiplicative seasonality. We also use backcasting for initialization because this is weekly data. So if we did optimization, we would need to optimize 52 seasonal indices, which is quite big. Backcasting simplifies things. It is not ideal solution, but it is a fast solution, and it is a solution. We're also saying forecast is equal to 13, so one, quarter ahead. Holdout true means that the data will be split into parts. And interval, we also ask for prediction intervals, and we also explicitly tell to our function not to be silent about the things that it does. So the output, I don't want to go into very many details on the output, but important things here are smoothing parameters, which are alpha and gamma, and they are quite high in this example, and information criteria, which is 2096, doesn't say anything on its own, but when we want to compare things, this is useful. And also, let's have a look at the error measures that are printed by the function. So, for example, scaled mean absolute error is 33.6%. And it looks like this. It's quite a poor forecast, isn't it? Because we're actually missing. The reason why it behaves like that is because the smoothing parameters were quite high, so the function adapted to the last observation and just jumped down. So this is an issue. What can we do? Let's start adding variables. In the beginning, we just add everything and we'd say extract promo data. So we add all the prices and promotions that we have. We feed the model. What do we have? The AIC has decreased, and SMA is now 14.3% instead of 33%. So we see an improvement, and this is something that we would expect. If we have explanatory variables, we add them, we are increasing the accuracy. And the graph looks like this, which is much better. But now the problem is that we've included everything. So it would be nice to include only those that are actually meaningful, right? So let's get rid of redundant variables. We do that using parameter xrec_do_select. What it does stepwise selection of the variables. And we get further improvement, not that much, but still a bit, 13.8 versus 14 with something, and the graph. So I say here perfect on this slide, which is actually not true, because we could also include lags and leads. When we're talking about promotions, people tend to buy during the promotion, but then when promotion ends, the sales will go down. But this is something for potential future improvement. We could have done all of that, not stepwise, but with just one line and with YYY here. YYY means that the function will select only between the pure multiplicative models. And in case of promotions, this is usually one of the things that we tend to use. So yes, include leads and lags. This is the first case, first example. The second one, previous was fast. Now let's go to slow moving products. And with slow moving products, the idea is quite interesting on its own, because on one hand we have uncertainty about demand sizes, on the other hand we have uncertainty about when demand will occur. And I'm showing you an example of a product that becomes obsolete. So it was sold okay in the beginning, but then people stopped liking it and stopped buying it. So we observe zeros happening in the data. But in this case, company was trying to do something, and they also had promotions. And people, when saw that the product they don't like anymore is on sale, well, some of them thought, maybe I should buy. And that's what they seem to do when red line appears. So we have quite difficult situation here, because we have several things combined all together in this example. What can we do? We start from the smaller thing. This is included in the package, the variable occurrence that tells the function that demand occurrence should be also taken into account. If you're interested about details, there is vignette on that explaining what are the models behind that. There is working paper, and there is one paper and a revision in IGF. So what do we have as the output? Once again, I don't want to go into many details, but smoothing parameter is very high again. This is just the level model. So if some of you are familiar with Croston method or TSB methods, that's what we have close to. So this is based on simple exponential smoothing, just level changing over time. And the error, where is it? Scaled MSE is 4%, for example. And that's how it looks. In fact, it's not actually bad, the performance, the default performance, because depending on what you really want, you might have different needs, and the function just produces you average demand in the future. But how can we improve it? Well, let's add explanatory variables here, and let's try multiplicative trend. What do we have then? The smoothing parameters go down, AAC goes down, scaled MSE in the holdout is 1.8%, and this is the forecast that we get. We see that the model now captures the promotions, and when it comes to the holdout, it also produces forecast for promotions. But it's not ideal, because currently we are only including the explanatory variables in the demand sizes. But demand occurrence, so when we are talking about the probability that people will buy, this does not take into account these features. So we do that using OES function, occurrence exponential smoothing. The syntax is quite similar to just exponential smoothing that we've seen before. What do we do here? Trend, multiplicative, and explanatory variables in the prediction of the probability of sales. That's how it looks on its own. So y-axis shows 0 to 1. And we see that probability is just declining over time. When promotions happen, it jumps up, but overall it just goes down. And we can use this in exponential smoothing. We insert our model here in occurrence. We get new output, 0.6%, so it went further down, and that's how it looks. So when we take into account all the information in two parts, not only demand sizes, but also demand probability, then we can improve our process. And that's what our function allows to do. Now I have two more case studies, but I don't think that I will have much time to do them, so I will jump through them a little bit. One of them is demand with multiple seasonalities. And we have multiple seasonal ARIMA model in our package, in Smooth package. It has different syntax than conventional ARIMA. And this different syntax allows you to include how many lags and orders you want. So here we have simple AR3 with lag 1, then we have seasonal AR2 with lag 48, and finally we have seasonal AR1 with lag 7 times 48. So we can make quite complicated things. An example is half-hourly electricity demand from forecast package. We feed the model, there is automatic selection. It takes just a little bit of time, and after 2,000 seconds doing things, we get the results. 2,000 seconds is probably close to 1 hour, I don't know. But this is a big data, so it takes time. And just as an example how it looks, it sort of makes sense because it managed to capture the seasonality in the day and in weeks. So I'm not saying that this is the best method. We would definitely need to compare it with the others and use some benchmarks, but that's what we have. We have some other options. We can use this exponential smoothing with explanatory variables and do something similar. Last, multivariate models, and very briefly about that. In some cases, you can have several products, right? And they have similar patterns, similar seasonality, similar trends, and so on. You could fit exponential smoothing for each one of them, but you could also do it just all together. And this is what vector model does. So we consider data as multivariate. There are different parameters also explained in vignettes. And as a result, you get forecasts for each of the time series, and they are somehow connected or related to each other. The last bit is ongoing research with Hui-Jing Chen and John Boylan. We don't have any paper for that, but John presented at ISF 2019, and we hope to finish it this year. What else? Some other features. There is complex exponential smoothing, the stuff that I developed during my PhD. Funny thing, very complex. There is state space constructor. I don't have time to go through these things, unfortunately, but there are some vignettes, and there are simple and centered moving averages, and finally, simulation functions. So you can simulate data from ETS, ARIMA, and so on with any parameters you want. That's all. Thank you for your attention, and I'm...
Questions, comments, wishes? I was a little bit curious about towards the end there. You talked about automated model selection, the one which took more than 2,000 seconds. I was a little bit curious how that was done, because maybe you said that, but I didn't get it. Did you select over both the lags of the armor part and the seasonality, and how is that implemented in practice?
I didn't say that, so thanks for the question. Yes, there is a procedure, building procedure. It goes through different parts. We actually have a paper with Photios Petropoulos on that, and probably mentioned it somewhere on slides. But the idea is that you're trying different orders of differences, then take residuals, different orders of AR, different orders of MA, and you compare information criteria, and in the end you select the model and re-estimate it. So that's what we do.
But because usually the conventional approach to a non-stationary model would both, if you treat the seasonality predicti as non-stationary, I think you might do that. Would you do that?
Do you mean that that usually tests are done?
You talk about seasonality, right? And you select in the
no,
yeah.
We
and
select between seasonal, non-seasonal as well.
But how do you specify? What is the underlying statistics of the seasonality part? How do you actually?
We use it. We do it using information criteria. AAC. Everything is done using AAC. So we do not do any statistical tests here.
Okay.
Yeah.